Friends, welcome to the 8th lecture titled Regasification Platforms under the NPTEL course on offshore structures under special loads including fire resistance. We were discussing about a new conceived idea of a platform by name offshore triceratops in the last lecture. We said that ball joints pose a great advantage in terms of isolating the deck. However, it is also important to estimate the rotation capacity of the joint under the given loading. For example, you have a joint which is going to rotate about this axis under a specific value m. So, one can try to plot m phi relationship for this kind of studies, where m is going to be the moment applied to the joint at this connection of CG and phi or let us say theta is a rotation. So, moment is m and theta is a rotation. However, when this joint is subjected to an axial load P, the moment rotation characteristics vary significantly. So, to estimate this, a experiment can be conducted which was tried on a scaled model at the research laboratory at IIT Madras, where the deck was connected to the ball joint fabricated to scale and the legs were associated to this joint. So, this is my ball joint, an additional arm introduced here was also imposed upon by a axial force of a known value, which is going to be the lateral load acting on the system, which is going to cause the moment, and an inclinometer is placed on the ball joint to measure the rotation of this ball joint or this buoyant leg with respect to the joint. A typical moment rotation curve is derived on a scaled model. I am giving the values on scaled model. So, 0, 2, 4, 6, 8 degrees, and Newton meter for a scaled model, let us say 1, 2, 3.0 etc. The typical curve remain linear to make us to realize that the ball joint will have less influence of the load P on its m theta curve. Rotation in the ball joint was measured using inclinometer, and when moment required for rotation is evaluated, and then the damping of the joint is also estimated. Friends, interestingly, in such cases, due to continuous rotation of the joint may also fail in fatigue. So, that can be seen as one of the important critical member where a criticality analysis can be done to design this joint carefully. To extend the study for better understanding, the Triceratop numeric model was subjected to aerodynamic loading. The typical mass matrix of the platform is of course 9 by 9, because 6 degrees for the support system and 3 degrees independent for the deck, because the deck rotations are not dependent on the buoyant leg rotation degrees of freedom. However, the deck translations are dependent on the translations of the substructure. Therefore, 6 degrees of freedom for the support system of buoyant legs and 3 independent rotational degrees of freedom for the deck makes it 9. So, let us say m1 plus ma1 additional mass remaining all where seems to be 0. Similarly, m2 m3 plus additional mass in heave degree m4 m5 m6 m7 m8 and m9. However, the pitch degree for unidirectional wave also resulted in added mass in m51 and ma53. If you look at the typical stiffness matrix, it is again 9 by 9, which has got let us say K1, K11, K31 and K51 and K81 and 0. Similarly, K22, K32 and K42, K72 zeros, and for heave it is K33 and all others were zeros, K24, K34 and K44 and K74, K15, K35 and K55, K85, K36 and K66, K27, K37, K47 and K77, K18, K38, K58, K88, K39, K69 and K99. So, it is a 9 by 9 matrix. Of course, the classical matrix C is worked out as A0m plus A1k, which is a Rayleigh damping model. Studies were conducted in numerical analysis and results were obtained. We will quickly discuss these results to realize how the behavior of this platform was very interestingly done. If you please pay attention to the raw plots, that is response amplitude operator in the surge and heave degrees of freedom, one can see here the plots are done for frequency against the spectral density in the vertical axis, whereas 4 plots are done: buoyant leg 1, set of legs 1, set of legs 2 and set of legs 3 and the deck. So, one can see here the deck response is fairly lower than that of leg 2 and leg 3, whereas slightly higher than that of leg 1 in the surge degree of freedom. In such degree, whatever may be the action taken by the legs are transferred to the deck. So, however, legs are independent of each other. There is no rigid body motion between the legs because they are not interconnected. The only element interconnects them is the deck, which is through the ball joint. So, qualitatively the peak occurs almost at the same frequency for all the members, whereas the energy dispersed along the frequency band for the deck is much lower compared to the 2 legs, ensures safe operability, and the deck remains almost horizontal compared to these 2 legs of 2 and 3 in such degree. However, interestingly, if you look at the heave degree of freedom, the deck response is more or less similar to that of the buoyant legs, ensuring that there is a comparatively a better rigid body motion in the vertical plane in the heave degree of freedom. Similarly, if you look at the pitch response amplitude operator, one can see here ball joints do not transfer the rotation from the substructure to the superstructure. Practically, the deck shows no response in the pitch degree of freedom, whereas the buoyant legs independently show different kinds of responses. One may wonder that why the deck is at all showing a response in pitch degree if the ball joint is capable of filtering or restraining the complete rotational degrees of freedom from the buoyant leg to the deck. Interestingly, this is resulting from the differential heave happening between the legs, because the differential heave also results in the differential heave of different buoyant legs results in pitch motion. I have a superstructure, I have a substructure, these are isolated, but the heave motion of this and this are different. Let us call this as heave 1 and this as heave 2, they are different. With respect to this plane, this difference causes rotation, though the rotation is not transferred because of the pitch rotation of the leg to the deck. Please understand, the pitch rotation of the legs are not transferred to the deck. Since heave is transferred, differential heave or difference in heave response between the legs causes pitch motion. of the deck. So, that is the reason why we also have a deck motion pitch response in the deck compared to the BLS. Therefore, one can say that Triceratops have heave restraint system because of this wave direction does not influence the response of the platform, provided three legs are symmetrically placed we also saw deck response is lower than the buoyant legs even in such degree, ensuring a better and safe operability in the case of rotational responses. Deck response is insignificant, ensuring better operability and a good recentering capability. Natural periods in surge, sway are slightly higher compared to TLP, making it more compliant. In heave, pitch and roll, they are similar to TLP. In yaw, is slightly lesser compared to TLP, but more or less similar to that of a spar. So, the system derives all advantages of TLP and a spar platform. The next system what we will see now is regasification platform. We know that when the crude oil is explored from the drilling or exploratory platform, when crude oil is explored, it is to be either stored or transported using a shuttle tanker. Now, storage is a big problem in complaint structures because it affects buoyancy, it also affects the weight. Therefore, the platform stability may be challenged. The second issue is these platforms do not have enough storage capacity also. So, it is an usual practice that the explored oil are generally transferred to the coast for further production either by pipelines or by shuttle tankers. When you transfer this oil produced oil or crude oil through pipes, large vessels, etc. This makes oil production expensive. What is the alternative? FSRU, floating storage regasification unit. Are seen as an effective alternative. So, people are now working on LNG terminals offshore. So, compared to crude oil, liquefied natural gas is a very successful alternative. Okay. This is ABS 2004, 2006. But there is a very main issue with the LNG production. The main issue with LNG is transporting LNG is very hazardous as per DNV 2010, 2011. If we attempt to transfer them or transporting them by shuttle tankers, there are many factors which are bothering us. One is the cost factor. Two, such transfers from the platform shuttle tanker cannot take place in all sea states. So, when the sea states are very rough, they have their own class of hazards. So, though LNG terminals are good alternatives, but platforms exploring, storing LNG need to be looked with a special attention. So, LNG platforms which houses regasification also needs special attention. So, by Benhua in 2013, it is seen that FSRUs cost lesser than 50% of that of onshore processing facility. So, it is expected that processing is done offshore. The conventional platforms what we have today like TLP, spar, etc., have very high displacement, degrees of freedom, they will not suit processing of LNG, because LNG terminals require a very high limitation in terms of rotational responses of the deck. So, a base isolated deck can be an alternative. So, a new platform is conceived, a new platform geometry is conceived, which we are going to discuss now, that is called buoyant leg storage and regasification platform. So, we say BLSRP. The foremost condition of an BLSRP as per class NK 2014 is it should have very minimum top side response under operational sea states. So, the condition here is deck response should be minimized. That is what the goal, that is the objective. So, the geometric form of BLSRP has got a deck supporting buoyant legs, but in this case they are not 3 but 6. To make it more symmetric with respect to wave direction. So, 6 buoyant legs support the deck. Deck and the legs are isolated by ball joints. Interestingly, buoyant legs are similar to TLPs because they have a taut moved support system coming from the tendons. They have a monolithic action between deck and the legs in translational degrees of freedom. This is similar to that of a spar. So, now BLSRP is again a combination of advantages of TLP and the spar. A typical schematic view of this structure is now shown on the slide. This consists of a deck which has all electromechanical components. Usually the deck is circular because the influence of the deck in terms of its area distribution or the mass distribution is more or less symmetric with respect to the CG. It has got a crane, helipad, living quarters, compressor units, regasification units, gas turbines, etc. Now, the deck, which is essentially stainless steel LNG tank, is isolated from the buoyant legs with that of the hinger joint. Is a hinger joint we have, and the buoyant legs one end is connected to the seabed using conventional tendons which is taut mode as you see in the case of a TLP. The typical structural detail which is investigated experimentally and numerically on the research point of view is on the screen. The investigation is carried out on 1:150 scaled model of a BLSRP for a water depth of about 600 meters. The mass of the structure, the mass of the tank, the plate are all resembling to a typical TLP topside. There are 6 numbers of buoyant legs with a ballast value of about 100 kg closer in 1:150 scale model. The diameter of the deck is about 100 meter in prototype, which is a very conventional dimension for a classical tension leg platform. Of course, in that case it may be a square or rectangular platform, but in this case the deck is intentionally kept circular. It is a deep draft system which is similar to that of a spar platform with a positive metacentric height which enables better stability. The structural properties of mass moment of inertia, radius of gyration, teeth diameter and modulus of elasticity are now shown on the screen, both for the deck as well as for a single buoyant leg for our understanding. These are some of the elements of the platform which has been fabricated for experimental investigation. These are the buoyant legs, these are the hinged joints or the ball joints. There is a hook at the bottom of the buoyant leg which is being used to do connection of the tendon to the buoyant leg and the seabed. That is a typical figure of the hinged joint. This is actually used to measure the teeth tension variation in the tendons. This is a spread leg mooring system with 6 legs being housed in the experimental facility. Is a top tension riser system where at the bottom they are connected to the reverse tension system and the tension in the legs are adjusted by the adjustable mechanism which is ratchet mechanism controlled from the top. So, the deck is now housed for instrumentation and now the buoyant leg platform with 6 legs in hinged joint connected to the stainless steel deck to a scaled model are now ready for experimental investigations. Free vibration analysis conducted on this very clearly shows the tethered and the prototype, free floating and tethered in terms of all degrees of freedom on the deck. So, one can very clearly see here the periods of degrees of freedom in terms of surge and sway resemble very closely to a tension leg platform, whereas heave now resembles closely again stiffness in the vertical plane, ensuring safe operability in terms of its safety for the minimum deck response in the platform. If you look at the typical time history response of the platform for 90 degrees and 1 seconds wave, 8 seconds wave, the surge acceleration and the heave acceleration measured on the deck and the BLS are shown on the screen. One can very clearly see the surge acceleration of the deck is minimum at all instances of time compared to typical buoyant leg 1, whereas the heave response is more or less same, ensuring rigid action connectivity or rigid body motion between the buoyant leg and the deck in the vertical plane. So, friends, BLSRP showed a rigid body motion in vertical plane and high compliancy in horizontal plane. So, the primary objective was to reduce the rotational degrees in the deck in terms of pitch, roll and yaw motion, which is now achieved by placing a hinged joint between the platform leg and the deck. So, one can understand here that the deck response is lesser than the buoyant leg or the supporting system in surge degree of freedom, which ensures a very good recentering capability, which is also desired for regasification platforms. To ensure a good recentering capability, please pay attention to the response shown on the screen now. The response in all legs and the deck are plotted for 90° wave approach angle for 0.1 meter wave height. The surge acceleration is plotted on the y axis, whereas the wave period is plotted on the x axis in seconds. One can see very clearly that the deck response is almost lower than all the buoyant legs, and this value is more or less attempting to close to come to 0. It is not practically coming to 0, the deck is not resting horizontally completely in such degree of freedom, but it is very close, which ensures a better recentering capability, and buoyant legs are not interconnected. Each one of them imposes different tether tension variation, which also results in pitch or roll responses of the deck, because T0 change improvises heave response, and heave on a vertical plane is transferred to the deck by the hinged joint. Similarly, if you look at the heave response now, heave response of the deck is anyway lesser than that of the buoyant legs, ensures comfortable and safe operation, and BLS response is comparatively lesser than the system because the system is taut mode. The joint creates of course a monolithic connectivity between the support system and the deck carefully by the design. The roll responses of the deck are far lesser than that of the buoyant legs, but still the response of the roll degree happens in deck. It is because for uneven distribution of the responses of these legs happening at the substructure. If you look at the tether tension variation in percentage, one can see here for different buoyant legs the responses in terms of T0 variation in percentage is different. However, the maximum variation seen in the analysis is about 21%, whereas the permissible limit goes up to 22% as per LBSRP. Therefore, there is no danger of tether pull out. So, no danger of tether pull out. Rotational responses of the deck are minimized, and that ensures safe operability for a typical regasification plant. Friends, please understand the responses what we saw for a triceratop and a LBSRP, they were for conventional loads, not special loads. We will also discuss their responses back again when we talk about special loads and see how do they behave even under special criteria of exceptionally high loads, wherein a TLP may fail, whereas these structures can still remain safe but not operational. So, in this lecture friends, we got understanding of a new kind of platform which is LBSRP. So, now we understand that offshore platforms are form dominated designs they are usually not function dominated. It is preferred that they remain compliant, but we need a hybrid design in sense compliant in horizontal plane, but stiff in vertical plane. We also saw when we isolate the deck responses are minimized. Therefore, this platform can be made suitable for ultra deep waters where the forces are much higher compared to the deep and shallow waters. We will now show quickly a video for you to really understand how isolation of the deck enables the deck to remain horizontal practically with good recentering capability. Please pay attention to the video shown on the screen now. One can see here in a triceratop model, the legs are independently behaving under the wave action, whereas the measured instrumentation very clearly shows that the deck is practically remaining horizontal, and one can see the inclination of these legs. The inclination of these legs are different, that is imposing different rotational degrees of freedom, but for all this surge action or sway action is happening, heave is restricted, and roll, pitch and yaw motions from the buoyant legs are not transferred to the deck completely. So, the deck remains horizontal and imposes a very good recentering capability, at least in rotational degrees of freedom. So, friends, in this lecture we learnt a new kind of platform of BLSRP useful for LNG or regasification platforms. We learnt advantages of these new generation platforms with respect to the structural form and their betterment in performances compared to conventional platforms which are designed in deep water facilities. We will proceed further to understand their response behavior under special loads in the coming lectures. Thank you very much.